Hello, Math 2 Extended. This is Mrs. Bricky, and this video is for Unit 7, Lesson 4. We're going to be graphing circles and ellipse. So, first of all, starting with circles, the definition of a circle is that it is the set of all points on a plane that are a fixed distance away from a center, and that fixed distance we call the radius. So, if you measure from this point, this center point, to a length of r away from it, and mark that point, and then just keep doing it and mark each point that's a distance of r away from it in every possible direction, you would have all these points, and these points would create a circle. Circumference formula and area formula of a circle are formulas that you should know and have memorized. Circumference, the perimeter of the circle, the equation for that is 2 pi times the radius, and the area of a circle, which would be the space that circle takes up. That area equation is pi r squared. We're not going to be using those two equations, but every time I can remind you of them, I want to, because you should have them memorized. Today we're going to focus on learning about the equation for a circle and how to graph circles on a coordinate plane. So the way that we can write and think about equations of circles is actually based on triangles. So if you think about any point on the edge of a circle, so here's one right here, you can draw a little, I'm going to call it a reference triangle because that's what we call it in trig, but you can draw a little reference right triangle. And for that triangle, the radius of the circle, which for the circle I have on the screen right now is a radius of 5, but that radius is the hypotenuse of the right triangle. And we can think about one of these right triangles for any point on the edge of the circle. So here's a point. I can trace a line down here, connect it to the center. I know that the radius is 5, and I've created this little right triangle where one of the legs is the x coordinate. Maybe I'll call that one x2. And we have a y coordinate for that point. Well, I'll call it y2 just to differentiate it from the other one. And so this circle, for every point on the edge of the circle, we could draw one of these right triangles. So we can think about the Pythagorean theorem here with all of these right triangles. So for this, the circle is all of the points such that the x coordinate squared plus the y coordinate squared. So I'm just thinking about the two legs of that right triangle, no matter which right triangle it is. But if I square each of those and add them together, that has to equal the radius squared. And for this circle, the radius is 5. So we would have a 5 squared, which means we would have a 25. And my circle that I'm sort of working with right now has a radius of 5, but that circle could have any size. It could be a radius of 1, it could be a radius of 6. So here's a more generic form where we really just have that r squared there. So this circle, something about it that is important is that it is centered at the origin. So let's try graphing one of these. This is the circle x squared plus y squared is equal to 16. So if we think about the center of that circle is going to be the origin, I'm going to mark it. And then the next thing you want to think about is how big is this circle? What is its radius? Well, in the equation, this is an r squared. It's not an r. So you have to think about like the square root of that number, or what number do I square to get 16 in order to figure out the radius. So this circle has a radius of 4. So what we're going to do is count out in each of our 4 directions, count out a distance of 4. So I'm going to count 4 to the left. I'm going to count 4 up, 4 to the left. I don't know my right and left. I'm so sorry. And then 4 down. And we're just going to mark those 4. And notice I didn't count like 4 diagonals or whatever. That would be weird. You just want to count like 4 to the left, 4 to the right, 4 up, and 4 down. And then if you connect those into a circle shape and just do your best circle that you can. Mine are never perfect, but we can from that sketch get the idea of the circle even if it's not perfect. So this circle that I just drew is centered at the origin, and the first one I showed you was centered at the origin, but really there's nothing that makes a circle have to be centered at the origin. We could have a circle over here or over here or anywhere. Circle could be centered anywhere. So we're going to now look at what if our circle is centered not at the origin? What would its equation look like? So here is a circle. This circle also has a radius of 5. It's not as apparent. Well, I mean, it can be apparent if you want to look right here. If we count the distance from the center to the edge, it's 5. But what I want to think about is what does this equation end up looking like? So I'm going to click right here on this right and bring up this right triangle, because just because it's not centered at the origin doesn't mean we can't think about a right triangle here. So I have the sides of the triangle labeled, but I really want you to understand why the sides are x minus h and y minus k. So I want you to imagine or picture, we can even put a number down if it helps us think about it, I guess. I want to think about, let's see, this x value. And we're just calling it x, but I mean, we could put a number to that. I can see on my coordinate plane that's 1, 2, 3, 4, 5, 6 and a little bit. Let's call it 6.2. And I can see here that my center is located at an x value of 2. When we're thinking about this right triangle in the circle, we want to know what is the length of that leg of that right triangle. And it's the distance between the x value and the x value of the center. So the difference between the x value on the edge of the circle and the x value at the center. So in this little example with my approximation, you can see that that distance is 4.2, but we get that distance by taking the x coordinate, so we're just going to call that x, and subtracting the center's x coordinate, which I'm going to write just an h below there. And we subtract those, just like I subtracted the 2 from the 6.2 to get 4.2. So one of our legs of our triangle is a length of x minus h. So in the Pythagorean theorem, we're going to replace that a with an x minus h because that's one of the legs of the triangle. And then, of course, it's squared. And so if we think about the other leg of the triangle, that's this distance here. Well, my height, 1, 2, 3, 4, 5. I'm going to call it 5.1. It's a teeny bit above 5. And then the height of the center here is 3. So you can see that that distance is 2.1. And we get that distance by subtracting. But we don't want to just be talking about this particular point. We want to be talking about just a general point on the edge of the circle. So we're going to call the height y, and the center's height is called k. So that turns into a y minus k for our height. And that is the other leg of the triangle. And again, we're thinking about right triangles, we're thinking about Pythagorean theorem, so we square that one as well. And then for the hypotenuse, that's going to just be the radius of the circle. So this is what it ends up looking like. So we've got the horizontal leg is squared plus the vertical leg is squared, and that's equal to the radius squared. And this equation, you'll get really good at using it as we're going to practice both graphing circles from the equation, and then we'll practice the reverse, which is writing the equation if we have a picture of the circle. Just a couple of spots to be careful of. Sometimes students forget to use powers here. So I think if you remember that it's based on the Pythagorean theorem, that can help you not forget the powers. Again, because it's based on the Pythagorean theorem, it is always a plus here. And then just be careful, it is an X here and a Y here. So another common error I see is that people just put X's in both of those spots, but it is, the first one is the X and the second one is the Y. Okay, so here's a circle to graph. We have the circle x minus 2 squared plus y plus 4 squared is equal to 9. So with the x, we can see the x coordinate of the center. So we've got a center at an x value of 2. And then with the y coordinate, we see the y coordinate of the center. Remember that you see a sign change here because it's really a y minus a negative 4. But that turns into a plus 4 when we write the equation. So our center is at 2, negative 4. And then for this equation, I see a 9 at the end. That's a 3 squared, so that means my radius is 3. So I count 3 to the right, 3 up, 3 to the left, and 3 down. And then once I have those 4 points, I can sort of sketch my circle as best I can. So a really important skill is just to be able to look at the equation of a circle and immediately identify the center and the radius. So we're just going to go through a couple of those. So when we inspect our equation, we can see the center's location is at 2, negative 3. And then this is my radius squared, so that means the radius of this circle would be 7, because 7 squared is 49. Next circle, I can see the x-coordinate of the center is at negative 4, and this one is a lot different than the one above. It doesn't have parentheses, it doesn't have a number. So when you have something like this, it's as if we have a y minus 0 squared. But when we have y minus 0 squared, it's not necessary to write the 0 because it doesn't change anything. And if all we have is a y that's being squared, it's not necessary to write the parentheses. So we just end up with this thing that looks like a y squared. So you have to kind of know that that means that the vertical shift or the vertical translation is 0. Okay, and then the last thing for this circle is that you can see that the r squared is 100 and 100 is 10 squared, so our radius is 10. All right, the last one, we look first for the center. This one has a center at negative 1, positive 5. The radius squared is 20. 20 is not a perfect square though, so we would have to take the square root of 20 to figure out the length of the radius. In exact radical form, that would be 2 root 5. So we do want to say that that's the radius. If you were graphing this though, you would want to figure out the decimal approximation of that. It's about 4.4, I think. If it's not 4.4, I'm sorry, I don't have a calculator in front of me, but it's somewhere close to that. Okay, we'll graph one in a second that has a irrational radius. So here we go, graphing this circle. We have a center at 2, 0. So here's my center. R squared is equal to 81. That means our radius is 9. So count 9 to the left. I mean, that's the right. I'm sorry, I don't know my right from left. I mean, I do, but I'm very slow and not automatic at it. And to the right. Oh, that was left. Oh my gosh. And down 9. So we counted 9 in each direction. The bigger the circle, the harder it is for me to draw. That's a terrible circle, but you get the idea. For this circle, we want to write down the domain and range. So remember, when we think about domain, we're thinking about x values from left to right. And for range, we're thinking about y values from the bottom to the top. So for domain, the farthest left side of this circle is at negative 7. And that is a point on the circle, so we want to include it. And then over to the far right, we've got the circle hitting a value of 11. That is a point on the circle, so we want to include it. So our domain is from -7 to 11. For range, we want to think about this circle from the bottom to the top. So we want to, the lowest value, sorry, my computer was being weird. The lowest value is -9, and the highest value is +9. And again, those points are part of the circle, so we want to include them. Okay, this circle is the one that has kind of the weird radius. So first we want to identify the center. The center of this circle is at -4, +2. Here it is. And the radius, well, r squared is equal to 10. So if we square root that, we just get root 10 for the radius. And square root of 10 doesn't simplify. In order to graph this, we kind of need to know like about how big it is. So if we look at the decimal approximation, it's like 3.16 or 3.2. So we're just going to go a little bit past the 3. In class, we talked about the domain and range of this circle, but for the purposes of the video, I am not. But you can see approximately what the domain and range are from the picture. Okay, for the purposes of the video, I'm going to skip these two, but if you are still not feeling comfortable graphing circles, let me know. This one's a little baby circle, radius 1. It's so cute. Okay, we're going to switch to going backwards now. If I gave you a description of the circle, whether in words like these two or whether in a picture form like these graphs, you should be able to write its equation, just working backwards from what we've been doing. So this first one, and I do think when you're doing this, thinking about the Pythagorean theorem helps. So with Pythagorean theorem, we should have something squared plus something squared equals something squared. And so that can kind of help you with the setup if you're ever not sure. So the first something in our equation is x minus the x coordinate of the center. And then comes our y minus the y coordinate of the center. And then the last part should be the radius squared. It's customary to not, whoa, my 1 just changed into a 2. It's customary to not write it with a power over here. We do want to actually square that. So it's x minus 1 squared plus y minus 2 squared is equal to 16. This next problem is a little bit different. There are 2 strategies that you can use to solve it. So maybe you just see center and you start writing and you're like, okay, this will be x plus 3 squared plus y minus 4 squared is equal to, and then you're like, wait, the radius isn't given to me. This one doesn't tell you the radius. So a strategy for this problem is to kind of sketch it. That's what I'm going to show you first. Center is at -3, 4. So here's our center. And we know that the circle goes through the point 1, -2. So that's this point. So our circle is like this, but the other side, of course, too. I just only sketched the little part of it. So you can see in the diagram that this is the radius. And we need to know how long that is in order to finish writing the sentence or the equation. Equation is a math sentence. Okay, so what you could do, if you've already gone this far in doing a sketch, you could just build yourself a little right triangle. And building that right triangle, you can see that the distance here, this horizontal distance is 4, and this vertical distance is 6. So we can think about Pythagorean theorem for that little triangle. It would be 4 squared plus 6 squared is equal to r squared. But something to kind of realize is that the thing that we want right here is r squared. So if I can just add these two things together, that gives me r squared. Normally, when we're doing Pythagorean theorem, we like add these together and take the square root, and that's r, and that's great. But we actually do need r squared for our equation. So we can add the 16 to the 36, and we get that 52 is r squared. So we will put the 52 here directly. So that's the equation of a circle with the center at -3, 4 that goes through the point 1, -2. Okay, I'm going to write this middle one, and then actually, I feel like I've already written that one. Let's write this first one, and then we'll skip to the last one. We'll skip the middle one. So I can see, and sometimes it's helpful to people to write down the center. I can see that the center is at -2, 2, and I can count that the radius is 3. So this circle would be x plus 2 squared plus y minus 2 squared is equal to, and 3 squared is 9. So that's the equation of that circle. I'm going to skip the middle one and go to this last one. We can see the center. So we can see that the beginning part of the equation would be this. But again, it doesn't directly show us the radius. It does show us that the circle goes through the origin, though. So what I'm going to do is just build myself a little right triangle here. And if this point is the point 3, -4, then this side of the triangle is 3, and this side is -4, or you can think of it as +4 if you want. And so this is a 3, 4, 5 triangle. 3 squared plus -4 squared is r squared. These two add together to give me 25. So in the equation, I have a 25, and that means the radius of the circle is 5. Okay. That is it for circles. So if you want to pause and work on some circle practice, that's great. We also need to graph ellipse. That's not going to be as intense as graphing circles. Little explanation, couple ellipse graphs, and we'll be done. So if you want to pause, you can for a minute and work on circles, or just plug on away and do the ellipse. Okay, an ellipse is a plane curve surrounding two focal points, such that for all points on the curve, the sum of the two distances to the focal points is constant. So kind of weirdly different from a circle. A circle has the center, and we talk about that the distance here is always the same no matter where we measure it. For an ellipse, we have to make two measurements. So we have these two blue points, they're called the focal points. And if I take a point on the edge of the ellipse and I measure these two distances, the sum of those two distances is always the same. So if I add little green piece to the little green piece, it's equal to the two red segments added together, and that's also equal to the two turquoise segments added together. And every point on the edge of this every point on the edge of this ellipse has those that same sum. So an ellipse is symmetric, though, so it does still have a center, and that's what the black point is. So it is symmetric about the center. So we're going to talk about the equation of an ellipse and learn how to graph them. Here's another just little visual of this idea of an ellipse. A circle actually is an ellipse. A circle is an ellipse that has the two focal points at the same spot. So right now I have a perfect circle here. If I take one of those focal points and start moving it away, this is almost a circle, but not quite. This ellipse has what we call a focal length of 16. So the green segment plus the pink segment, maybe that's purple, I don't know, equals 16. And no matter where I rotate that point to on the edge, those two distances are going to always add up to 16. And, if I spread those focal points farther apart, the farther apart they are, the more we call it eccentric, the more eccentric the ellipse is. So I kind of have it almost too far over there. Hold on, give me a second. So the closer the focal points are to the edge of the ellipse, the sort of longer and skinnier it is. So this ellipse has a focal length of, or focal distance of 24.75, and no matter where I put point D, those two distances together always add up to 24.75. These are hard to draw on paper. Usually you use string and pin down the string at the focal points, but it is kind of difficult to draw these. Not as easy as drawing a circle. But graphing these is as easy as graphing a circle when we have a coordinate plane. So when we graph them, we use the center and then we use what's called the major and minor axis. So a circle, like this top drawing right here, it has the same major and minor axis. So when we graphed these, we would count out like 3 and 3. But with an ellipse, we might be counting out different distances. Like we might count out 4 and 4 in the x direction, and then 6 and 6 in the y direction. Or we might count out 5 in the x direction, and we might count out 2 in the y direction. And that's what gives it sort of the squished shape of an ellipse. So I want to start with this ellipse equation on the left, and then we'll relate it to we're going to start with the circle on the left, which is an ellipse, and then we'll talk about the ellipse on the right that's in blue. So I have the equation of this circle right here, x minus 2 squared plus y minus 1 squared is equal to 9. An ellipse equation is kind of different from a circle equation because in almost all ellipse equations, and definitely all the ones you will deal with in this class, this number has to be a 1. It's always, an ellipse equation is always equal to 1. So right now the equation we have is a circle equation with an r squared. To turn that into an ellipse equation, we're going to divide both sides of our equation by 9. And when we do that, on this side, we've got two things being added together, divided by 9, and we are allowed in math to separate that. So I'm going to separate them into their two terms. And on this side, 9 divided by 9 is 1. So this second equation that I've written, it is the equation of this exact same shape if I was thinking of it as an ellipse. So circles and ellipses are kind of like rectangles and squares. Every square is a rectangle, but not every rectangle is a square. So every circle is an ellipse, but not every ellipse is a circle. So this is the circle equation for this red shape. This is the ellipse equation for this red shape. So I want to compare this second equation to the equation of this blue ellipse. Here is the equation of the blue ellipse. And you can see they do have a lot of similarities. They both have an x minus 2 squared and a y minus 1 squared, and that is marking that center of both of the shapes. So something that is different about them is that the circle has the same number on the bottom of both of its fractions. And on the ellipse, those two numbers are different from each other. They do both, something they have in common is that they both have that 1 at the end. So what these numbers that are underneath the part of the equation that shows us the center is that they're telling you how much to count out in the x and y direction. So it's not a radius because it's not a circle. So we usually call it an a squared and a b squared. And so this one is telling me count out 3 in the x direction. And this one is telling me count out 3 in the y direction. So when those two numbers are the same, it gives you this circle because you've counted out the same direction or the same amount in each direction. For this equation, my a squared is 16. So that tells me to count out 4 in the x direction, both directions. And it tells me to, this is my b squared over here, that tells me to count out 2 in the y direction. So I count out 2. And because those distances aren't the same, it gives us this ellipse shape. Okay, so we're going to graph 2 ellipses and then we're finished. This first ellipse, the center is at -2, -3. So you see that almost identical with how we find the center of a circle, -2, -3. So this 25 is a 5 squared. It's underneath the x coordinate or the x part of the equation. So we're going to count out 5 in the x direction. 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. And then in the y direction, so with the y part of the equation, I have a 9. That's a 3 squared. So I'm going to count out 3 in that y direction. 1, 2, 3, and 1, 2, 3. And then if I can sort of connect those into that ellipse shape, I'm not very good at drawing these. That's our ellipse. So let's practice that one more time. I've got x minus 5 squared plus y plus 4 squared over 16 is equal to 1. So we want to start with the center. The center of this ellipse is 5, negative 4. And shoot, the first one's not even a fraction. Well, if there is something that you're expecting or wanting to be a fraction that is not a fraction, it is a fraction over, it has a denominator of 1. It's over 1. So in the x direction, we're going to count out 1. So it's going to be a skinny guy. And then underneath the y part of my equation, I have a 16. That's a 4 squared. So in the y direction, I'm going to count out 4. 1, 2, 3, 4. 1, 2, 3, 4. And so we get this ellipse. When you're doing the ellipse on the assignment, I think there is a couple that ask about the domain and range of an ellipse. That will work exactly the same as for a circle. All right, that is it. You're now an expert at graphing circle and ellipse. So just let me know if you have any questions. Thanks for staying caught up in class.